Let me also share my screen. Okay, so we are live. All right, so we're going to proceed with our discussion of the third chapter, which deals with the principles of equilibrium, dynamic equilibrium. We started discussion of it, of course, and then, of course, you were supposed to watch the video lectures concerning the rest of the chapter. So again, as usual, the first question I have to ask is, are there any questions? Anything that you need explaining concerning those videos? Any questions? Excuse me. Any questions? Okay, so there are no questions. Let's proceed to look at assignment number 3. And in assignment number 3, the first question has to do with equilibrium constant expression. So let me just say a couple of things about equilibrium constants, which I don't think I got to discussing, but of course, the videos will explain all of that. So if you have an equilibrium system, and this is purely hypothetical, AA plus BB to give CC plus DD. Okay, so the lowercase letters represents the coefficients, and the uppercase letters represents the formulas for the different substances. So therefore, Kc, the equilibrium constant, would be equal to the concentration of C raised to the C times the concentration of D raised to the lowercase d, divided by concentration of A raised to the lowercase a times the concentration of B raised to the lowercase b. Now, the assumption is that these are all equilibrium concentrations. So we're assuming that the system is already at equilibrium, all right? So if the concentrations are equilibrium concentrations, which means that they don't change over time, that means that you have the continual back and forth where the rate of the forward reaction is equal to the rate of the reverse reaction. Then when you put those terms into this equation, you're going to get a constant. And this constant is constant as long as the temperature is constant. So let me just add here at constant temperature. All right. So that's basically, in some textbooks, they call this the equilibrium law or the law of mass action. Equilibrium law or law of mass action. All right. So that's basically what we'll be dealing with question 1. Now, before we move on to the actual question, couple of things I want to say about this equation. If there are any liquids or solids present in this equilibrium system, then those terms would not appear in this equation. So let me give a quick example. Let's say, for example, you have a reaction where, I'm trying to think of a good one. Okay, let's do this one. N2O4, which is a gas, in equilibrium with 2NO2, which is also a gas, all right? Now, in this case here, Kc will be equal to the concentration of NO2 squared divided by the concentration of N2O4, and that's basically it, all right? So we're just following the guideline established by what we looked at up here, all right? So that's basically how you'd write down the expression for Kc for that equation, all right? And you'll notice that all the components are gases in this particular case. So this, whoops, this is a gas, and this is a gas right here. Why is this thing not responding? Hold on. And this is a gas right here, all right? I think there's something wrong with my tablet. But anyway, now let's say, for example, you have, let me see here. I'm trying to think of a good example. A good example would be, okay, AgCl solid in equilibrium with Ag plus aqueous plus Cl minus aqueous, all right? Now, in this case here, based on what we have covered so far, you would be tempted to write down that Kc, in this case here, would be equal to concentration of Ag plus times concentration of Cl minus, all right? Divided by concentration of AgCl solid, all right? So you might be tempted, and understandably so, to write down an expression for Kc looking like this. However, in this particular case, since we have a solid here, as I said before, we're talking about, in this case, whether or not there's a solid or a liquid. Because silver chloride exists as a solid in this system, we completely ignore it. And the argument behind that is that solids and liquids, as far as they are concerned, their concentrations are constant. So that value, whatever it is, would be basically be a part of the Kc expression right here. So when it comes to this particular system, we simply write down that Kc is equal to concentration of Ag plus times the concentration of Cl minus, and that's it, all right? So that's basically how you'd determine, or I should say how you deal with solids and liquids, right? So what we did here for the solid silver chloride, you'll do the same thing for any system that contains a liquid, all right? Okay, one more thing I want to talk about when it comes to equilibrium constants. And is it okay for me to get rid of this? Is it okay for me to get rid of this? Anybody? I just need one person to say yes or no.
Yep.
All right, so let me go here. If you're dealing with a totally gaseous system, right, we can write down an alternative equilibrium law based on what is known as Kp. Now, Kp is the equilibrium constant in terms of partial pressure. In terms of partial pressure, all right? And in this case, we use the pressure terms for the different components in the system. And I'm going to go back to the example I showed you before, N2O4 to form NO2, two of them. And this is totally gaseous, right? So in this case here, if we're going to write down an expression for Kp, that would be equal to the concentration of NO2 squared divided by the concentration of N2O4. All right, I'm sorry. I'm really screwing up this time. Shouldn't be concentration, should be pressure. So let me just erase all this here. And let me go back here. So this should be pressure of NO2 squared divided by the pressure of N2O4. All right? So Kp would be equal to this, and Kc would be equal to what we had before, concentration of NO2 squared divided by a concentration of N2O4, all right? So one might ask, what, if any, is the relationship between Kp and Kc? And the answer is that the relationship between Kp and Kc is Kp is equal to Kc times RT raised to the delta N, all right? Now, let me explain what delta N is. Delta N is equal to the sum of the coefficients of the products minus the sum of the coefficients of the reactants, all right? So to apply this to this system, Kp would be equal to Kc times R, which is the molar gas constant, by the way, times T, which is the temperature in Kelvin. And then up here, you're going to have delta N. Now, for this system, the sum of the coefficients of the products will be 2, and the sum of the coefficient of the reactants will be 1. So therefore, this will be 2 minus 1, which means that this would simply be equal to Kc RT, right? So the relationship between Kp and Kc is given by this equation for this reaction, all right? Okay, so with that said, any questions about what I just discussed? Any questions? Any questions? Okay, so let me, whoops. Oh, shoot, why did I, okay. So let me get out of this here. And get to the assignment number 3, all right? So the first question says, write the equilibrium constant expressions Kc and Kp for the following reactions, all right? So based on what I just discussed, you should be able to answer this question. So let me get my writing thing in order. Okay, so let's hear what you have to say about the A part, 1A. Anybody? Let's start off with Kc. What would be the expression for Kc? Let me remind you, for the reaction A plus B to give CC plus DD, Kc will be equal to the concentration of C raised to the C times concentration of D raised to the D, all divided by concentration of A raised to the A times concentration of B raised to the B. All right, so this is what you're going to use as your guide for answering 1A. All right, so
is there concentration HI raised to the second power?
Okay, concentration of HI, whoops, raised to the second power divided by
concentration H2.
Mm-hmm. Anything
and
else?
then concentration I2.
Exactly. All right. So that's basically how you do the Kc. Now the question also asks for the Kp expression. So what, based on this equation, would Kp be equal to? Well, anybody?
So I noticed when you were writing it down, the on the Kp, it had the NO2 on top and the NO2O4 on the bottom. So it's going to be the the reactants on the bottom and the products on top, correct?
Exactly.
Okay. So it would be the pressure of HI squared.
Okay, very
on
good.
Top. And the pressure of H2 plus the pressure of I2 on the bottom.
Well, not plus, it's times actually.
Oh, times on that. Okay.
Yeah, right. And that's it. That's the relationship. That's the, not relationship, the that's a Kp expression, right? So we have the Kc and the Kp expression. All right. Now the question did not ask for this, but let's do this just for the sake of it. Suppose the question is asking for the relationship between Kp and Kc. Now remember, the general equation for the relationship between Kp and Kc is that Kp is equal to RT raised to the delta n times Kc. All right? So that's the relationship between Kp and Kc. So, and remember what delta n is equal to. Delta n would be the sum of the coefficients of the products minus the sum of the coefficients of the reactants. So if I were to ask you, based on what we have done so far, the relationship between Kp and Kc, what would be the answer? Kp is equal to what?
To Kc.
I'm sorry?
Is it equal to Kc?
Okay, how did you get that? I'm not saying you're wrong. I just want to know how you arrive at that answer.
Isn't that what you told us the last slide?
No. What I told you just a while ago would be for a different reaction. I'm asking for the relationship between Kp and Kc for this reaction. So this is what we're using as our guide right here.
Would it be still it equals Kc because the difference in the coefficients of the products and reactants is 0?
Exactly. You're absolutely 100% right. Because if you're to use the same equation here, delta n in this case would be equal to 0, right? Because the total sum of the coefficients of the products is 2, and the total sum of the coefficients of the reactants is 1 plus 1, 2. So that would be equal to 0. So you're going to have 0 here, and you're going to have Kc here. And we all know anything raised to the power of 0 will be equal to 1. So therefore, in this particular case, Kp will be equal to Kc, all right? And this is something that you'll notice whenever you have an equilibrium system where we say that the equilibrium system is equimolar. What that means basically is that the number of molecules on both sides, or the number of moles on both sides, is the same. Whenever you have that situation, then the Kp will always be equal to Kc. All right? So that is just something as an aside that you should be aware of. Okay. Any questions about 1A? Any questions? Any questions about 1A? Any questions? Okay, so let me get out of this here. I'm going to okay, can I clear this? Okay. So let me do this. Let me scroll down. Okay, so let me hear what you have to say about 1B. Scroll down some more. Okay, 1B.
It'd be concentration.
Hold on, 1 minute. I'm sorry. Hold on. This thing here is not cooperating. Okay, so firstly, let's do Kc.
It'd be concentration HCl raised to the 4th power.
Okay.
And then concentration O2.
Multiplied by the concentration of O2. Remember, you're multiplying those terms, right?
Right.
Over.
And then concentration H2O raised to the 2nd power. And then multiply it by Cl2 raised to the 2nd power.
Exactly. And what would be the expression for Kp?
Pressure of HCl to the 4th power times pressure of O2 over pressure H2O to the 2nd power times pressure of Cl2 to the 2nd power.
Exactly, pressure of CO2 squared. Okay, and that's basically how that is done, all right? Any questions about this one? Any questions? Any questions? Minute here, check something. Okay, so I take it I can clear this, all right? Okay, what about the C part?
Well, for the KC value,
Mm-hmm.
it would be the same concentration, NOBR raised to the second power. And then
hold on 1 minute. NOBR raised to the second power divided by
concentration NO raised to the
And-
second power,
okay,
and then concentration BR2.
concentration of BR2. I must apologize. I don't know what's going on with my writing stylus here. Okay, and of course KP would be equal to what?
It would be the pressure of NOBR squared.
ENOBR squared divided by
Divided by the pressure of NO squared times the pressure of BR, or
okay.
sorry, the pressure of NO squared times the
Oh.
pressure of BR2.
And I just realized I made a mistake over here. This should not be squared. So let me erase that right now. Let me correct that. Yeah, this should not be squared. I don't know what I was thinking. All right. And that's basically how that is done. All right, let's see here.
I have a question.
Yes, ma'am.
When you're doing the KP and there's two molecules on the bottom, would it be okay to put like parentheses between the two to show the multiplication?
yeah, that's
instead of
fine.
me?
Yeah,
Okay.
that's fine too. Yeah, that's fine. No problem with that. I have no problem with that. Okay, any other questions before I move on? Any other questions about this before I move on? Okay, let me clear this. And let me do this and let me scroll down. I think there's only one more. Oh, we did this one already, right? Do I need to do it? I don't think I need to do it. I accidentally chose that as an example. So I'm just going to leave that alone. You can write your answers on your own assignment because we just covered this a while ago. Okay, now before I move on to question number 2, one thing I want to say about the value of KC, even though, as you all should know by now, I'm a stickler for units. When it comes to calculating the KC value based on the KC expression, the now accepted practice in chemistry is that we don't write down the units, all right? That was not the case when I was in college. Back in those days, we had to be concerned with the units for KC and also KP, all right? And also for the other Ks that you're going to learn about. You're going to learn about some other equilibrium constants later on. But the accepted practice now is that we don't write down the units. We just simply do the calculations based on the equation and write down the final numerical answer. And an example of that is shown right here, right? They gave this equation right here, and they say that the KC for this equation is 0.145, all right? So that is something that is basically typically what you'll observe when it comes to calculating, or if you're given the numerical value for KC or KP or the other equilibrium constants you're going to meet. Okay, another thing I want to mention, which is the focus of this question, is that the KC numerical value is actually dependent on the equation that you're using, right? So for example, in this case here, you'll notice that you have 2 NO reacting to form N2 and O2, right? And the KC expression is equal to 0.145. If you were to change these coefficients, for example, if you were to divide this right through by 2, then that will change the value of KC. So let me give an example using the same equation right here. Let me go to my writing thingy. All right, I'm going to do it up here. So let's say that instead of this equation, you're going to have NO to form half N2 gas plus half O2 gas, right? Now, if I were to write down the Kc expression for this, Kc would be equal to the concentration of N2 times the concentration of O2 divided by concentration of NO squared, right? So my question to you is, what would be the Kc expression for the equation written in this way? Kc would be equal to what? Anybody?
Would it be half of 0.145?
No. I'm not asking for that yet. I'm asking for the case, just like we wrote down the Kc expression here for this equation. I want to get a Kc expression for this equation.
Oh, so it would be the
Mhm.
concentration of N2 to the half power
Okay, very good.
and the concentration of O2 to the half power
Very good.
over the
Mhm.
concentration of NO.
Very good. Okay. Now what I'm going to do to make a distinction between this Kc and this Kc, I'm going to call this Kc Kc prime. All right. Okay. So this is what I want you to answer, right? And this will be, of course, based on your algebra experience. All right. If Kc prime is equal to what we have here, and Kc is equal to what we have here, then my question to you is, what is the relationship between Kc and Kc prime?
Kc is equal to Kc prime squared.
Exactly. Kc will be equal to Kc prime squared. All right. And the reason why we can say that is that another way of writing this would be this would be equal to concentration of N2 times the concentration of O2 divided by concentration of NO squared, all raised to the half power, right? So therefore, that would mean that all this right here would be equal to Kc, right? So therefore, Kc prime, based on this, would be equal to Kc raised to the half, which means that Kc raised to the, which means that Kc would be equal to Kc prime raised to the 2, all right? So that's basically the relationship between Kc for this equation, this original equation, and Kc for this equation. And you'll notice, right, that if I were to, how should I put it? Okay, so let me avoid confusion. Let me just erase this arrow right here. If I were to stick to this way of writing down the relationship, right, you'll notice that to get from this equation to this equation, what we did was that we divided everything by 2, all the coefficients by 2. Or another way of saying it, we multiply all the coefficients by half, right? So basically, we have the half up here as a subscript, right? So basically, if you multiply the original equation by a value, then basically the Kc prime value would be equal to the Kc of the original equation raised to the value that you raised the power to. So if I were to multiply this by n, then the Kc prime would be equal to Kc raised to the n, all right? So that's the relationship between Kc and Kc prime. If to get from this first to the second equation, you multiply by a certain number. And the number could be an integer like 2, 3, 4, or it could be a fraction like a half, a third, whatever, all right? Okay, so I just thought I should mention that. All right, is it okay for me to clear all this? Is it okay for me to clear all this? Going once?
Yes,
Going
sir.
twice? Okay, all right, so let me do that. Do this, scroll down. Okay, So again, we're starting from this equation here, right? And the question is now asking for the related Kc value. Now, in this case, they gave you the 0.145. Oh, I should have mentioned, going back to the, how could I forget? Going back to the previous example. So I won't rewrite all that I had before. I'll just write on this. Remember, we said that Kc prime is equal to Kc raised to the half. So in this case here, since Kc is equal to 0.145, 0.145 raised to the half would be the answer for Kc prime. Let me see what I gave, 0.145, and then hold on, 0.145, and then I find the square root. So the answer I would get here is 0.380, all right? So that's basically how you can determine Kc prime if you know what the original value of Kc is for the first equation. So based on what we have covered so far, let's look at A. Now in the case of A, you're given this equation for which you need to find Kc prime, and you're given the Kc for the original equation. So my question to you is, what would be the relationship between Kc prime and Kc? In other words, what is Kc prime equal to in terms of Kc? And let me help you out here by asking another question. Compare this equation to this equation. What are the differences between those two equations? And the hint I'm going to give you is that there are two differences, two important differences.
The first difference I see is that the products and reactants are reversed.
Exactly. Very good. All right. So what were the products in the first reaction would be the reactants in the second reaction and vice versa. Okay. That's the first difference. What's the second difference? What's the second difference?
I don't know if this is right, but maybe the possibility that there's two reactants in the second equation making one product versus the first equation has one reactant making two products.
That's kind of the same thing as what you said before.
Okay.
But there's another important difference. One that's different from what we just said. Anybody? Let me give you a hint. Compare the coefficients. Compare the respective coefficients. Well, oh, you know something? I'm thinking of the wrong question. I'm sorry. There's only one difference. Okay, I'm sorry about that. There's only one difference, folks. Okay, so how would we determine the relationship between Kc and Kc prime in this case? The only difference between them is that the products of the first equation is the reactants of the second equation and vice versa. All right, let me help you out here. The Kc expression for this is concentration of NO2, concentration of N2 times the concentration of O2 divided by concentration of NO squared, right? What's the Kc expression for this equation in A? Anybody?
The concentration of NO squared over the concentration of N2 times the concentration of O2.
Very good. So now that I've shown you these two expressions, what is the relationship between Kc and Kc prime?
Kc is 1 over Kc prime.
Exactly, or Kc prime is equal to 1 over Kc, which is what you want to find. You want to find Kc prime. So basically, Kc prime would be 1 over the value of Kc, which is given as 0.145. So let me do the calculation. 1 divided by 0.145. And according to my calculations, this works out to be equal to 6.70. All right. So that's the answer for question 1A. Okay. Any questions about this example? Any questions?
So
Any
if
question?
we're solving this, we have to write out, like for the actual answer, is it 6.70 or is it the Kc prime equals 1 over Kc equals? Like,
Well, it would have to be 6.70 because they
Okay.
gave you the Kc value. So it's not
Okay.
enough. It's not enough for you to write this down. Now, if the question just asks for the relationship between Kc prime and Kc, then of course you just write this equation down right here. But they gave you the Kc value. So presumably you need to know what, or you need to determine the Kc prime answer. All right, the actual
Okay.
numerical answer. Okay, any other questions about this? Any other questions? Okay, let me clear this and scroll down. Okay, so again, whoops, we need to find Kc prime for the second equation, which is this one right here. Okay, so what's the expression for Kc prime for this equation? That would be equal to what?
concentration of N2 squared times concentration of O2 squared divided by concentration of NO to the 4th.
Okay, NO to the 4th. Now, Kc for the original equation, I'm going to write this up here. Kc for the original equation is concentration of N2 times concentration, oh, by the way, this should be squared, can't forget that. Concentration of N2 times concentration of O2, all divided by concentration of NO squared. So based on what we see here for Kc prime and Kc, what's the relationship between the two? Kc prime would be equal to what?
Kc squared.
Kc squared, exactly. And then we put the number for Kc in this equation, that would be 0.145 squared, which works out to be equal to, according to my calculation, 0.0210. All right. Okay, and then now, for this equation, the Kc, let me write the Kc prime expression there. Kc prime would be equal to concentration of N2 raised to the half times concentration of O2 raised to the half divided by concentration of NO. So this is Kc prime, this is Kc. So based on those two, what's the relationship between Kc and Kc prime?
Kc prime equals Kc to the half power.
Exactly, Kc to the half power. So now it is 0.145 raised to the half. And according to my calculations, this works out to equal to 0.0210. 0.381. All right. So that's the answer for the C part. Okay, and there's a D part, but I want to make sure that you got this down. So let me know when it's okay to clear all this.
On the B part, is that equal to 0.0210?
Yes, indeed.
Okay.
Yeah. Mhm. Okay, can I clear this?
Yes.
Okay. So let me do this. Let me scroll down. And the last one is D. No, hold on. We just did D, right? No, we did C. So in the case of D, right, what would be, okay, hold on. Let me get my thing working here. Okay, so what would KC prime in this case be equal to? KC prime would be equal to what? Anybody?
Concentration of NO over concentration N2 to the half times concentration O2 to the half.
Okay. Now, if you notice, the KC for the previous one, for the E part, I'm sorry, for the C part is KC is equal to concentration of N2 raised to the half times concentration of O2 raised to the half divided by concentration of NO. So what I'm going to do is, to avoid confusion, this was the KC prime for that one. I'm going to call this KC double prime, all right? This is what we want to find. So my question to you is, what's the relationship between KC double prime and KC prime?
They're inversely proportionate.
Well, inverse.
It's like 1 over KC prime.
Exactly. So the answer that we got for the C part was 0.381. So I'm just going to put 1 over 0.381. And according to my calculations, the answer becomes 2.62. Oops. And that's basically how you do that. All right. Okay, so this is a good exercise in writing down and determining the relationship between different KC values for related equations. All right. Now, one thing that just occurred to me before we leave this is that I did not give a question. I don't think there's a question I've given you in this assignment where you have two equations that you need to add and how you determine the KC value. So let me do a quick example. Let me get out of this here. Well, let me clear this first. And then let me,
I have a question.
yes, ma'am.
When you're dealing with these types of problems,
Mhm.
are we worried about significant figures?
Yeah, because in all these examples, or in all these questions, the first number was given written to 3 sig figs. And basically all the operations are either squaring or square root or 1 over. In each case, you have to round off your final answer to 3 sig figs.
Okay.
All right. Okay. I'm trying to think of I'm not good at creating examples on the fly, but I'm going to try in this case. So let's say, in fact, let me do a hypothetical. So let's say you have A plus B to form C, and let's say C will react with D to form E, all right? So this is just purely hypothetical. And let's say this is KC prime, or just, I'm sorry, this is KC. Let me erase this here. All right, so the equilibrium constant for the first equation is KC, and the equilibrium constant for the second equation is KC prime, all right? So if you add these two equations together, right? As you should know from your previous Chem 1 experience, whenever you're adding two equations together, you cancel out those items that are common to both sides, right? So the result of that would be A plus B plus D to give E, all right? So the question is, what is the equilibrium constant for the final equation? Now, to answer that, what I'm going to do is write down an expression for Kc for the first equation, which is concentration of C divided by concentration of A times concentration of D. And then for the second equation, it would be concentration of E divided by concentration of C times concentration of D. Now, for Kc double prime, the Kc expression for that would be concentration of E divided by concentration of A times the concentration of D times the concentration of D. All right. So my question to you is this: based on these three expressions, the three different Kc expressions, what would be the relationship between Kc double prime, Kc prime, and Kc? Anybody? What would be the relationship between Kc, Kc prime, and Kc double prime? Let me just clean this up a bit. So this is concentration of D. I'm messing up. Okay, concentration of D. All right, so what's the relationship you think between these three terms, Kc, Kc prime, and Kc double prime?
Be Kc double prime equals Kc times Kc prime.
Exactly, you're absolutely right. And the reason why is because Kc is equal to concentration of C divided by concentration of A times the concentration of B. So that's Kc multiplied by Kc prime, which is equal to concentration of E divided by concentration of C times the concentration of D, right? So when you multiply these two terms together, you're going to get the concentration of C canceling out. And the final answer is going to be concentration of E divided by concentration of A times the concentration of B times the concentration of D, all right? Which is Kc double prime. And you'll notice that what cancels out here and here is the concentration terms for the intermediate C, which will be canceled out here and here when you're adding those two equations together to get the final equation, all right? So this is what happens when you multiply, when you add two or more equations together, right? The final Kc, let me just put something in a box right here. So if you're multiplying n equations, right? In this case, we were doing two, but this applies to any amount of equations. Then the new Kc value, I'm going to call it Kc prime, would be equal to K1 times K2 times K3 all the way to Kn, right? So basically, to get the final overall KC value, you're just going to multiply all the K values for the individual equations that you're adding together, right? So that's one more thing you need to take into account, which unfortunately I've not provided a question which deals with that, but that's something you need to be aware of. Okay, we're going to take our first break and we're going to resume at 11 o'clock, all right? I need to stretch my legs. So see you soon. Okay, I am back. So we're going to move on to question number 3. And in question number 3, as you can see here, it's asking for you to express Kc in terms of Kp for the following reactions. So if you recall, I said that the relationship between Kp and Kc is I'm going to squeeze it up here. Kp is equal to Kc times RT delta N, all right? So if you want to find Kp in terms of Kc, that's the expression. However, the question is asking for you to express Kc in terms of Kp. So in other words, what is Kc equal to? Can somebody tell me? If Kp is equal to what we have here on the right side of this equation, then what is Kc equal to?
Would it be Kp over RT to the delta N?
Exactly. So basically what all of these questions come down to in terms of answering them is finding out what delta N is in each case and just plugging that number there, and the result would be the relationship that the question is asking for. So what is delta N for this equation? Let's start off with that one.
Two.
You sure? Remember, delta N is sum of the coefficients of the products minus sum of the coefficients of the reactants.
-2.
Exactly, because delta N is going to be 2, which is the sum of the coefficients of the products, minus 3 plus 1, which is 4. So -2 would be the answer. And then we just put that -2 where delta N is and get the question answered as required. So Kc would be equal to Kp divided by RT raised to the -2, or you can rewrite this as Kp times RT squared. And that's it. All right. Okay, any questions about that one? Any questions? Any questions? Okay, so what would be delta N for this equation? Oops, something is wrong with my thing. Okay, what is delta N equal to in this case?
1.
Exactly, 3 minus 2. So what is Kc equal to as a result?
It would be Kp over.
I'm sorry,
RT.
repeat that. You sounded muffled.
It would be Kp divided by RT in parentheses. Or
Okay.
not even needed.
Yeah, right. Because it just be RT, right?
Right.
Raised to the 1, which is the same thing as RT. Okay, very good. What about C? What is delta N equal to in this case?
-1.
-1, because it would be equal to 2 minus 3. So therefore, Kc would be equal to what?
Kp over RT to the -1.
Exactly. Kp over RT to the -1, or we can rewrite this as Kp RT. Kp RT. All right. Okay. Let me clear all of this here and scroll down. Okay, so what is delta N for this one? So delta N is equal to what? It's going to be equal to 4 plus 1, which is 5, minus 4 plus 5, which is 9. So that's equal to -4, right? So what is Kp equal to in this case? I'm sorry, Kc. Kc, what is Kc equal to?
KP over RT to the -4.
RT to the -4, which is also the same thing as Kp RT raised to the 4. Okay, so that's basically how that is done. Now, let me just say here that I think I mentioned it before, but it's worth mentioning again. The temperature must be in Kelvin. And the R, I don't know what's going on with my tablet here. And the R value that you're going to use is 0.0821 liters atmospheres per mole Kelvin. All right. So that's what you need to be aware of. And the reason why I mention this is because you might have a question where you're actually given values of Kp and you're asked to find Kc or vice versa. In which case you need to know what the temperature is in Kelvin and you need to use this R value right here. Okay, so much for that.
A question.
Yes, ma'am.
In Chem 1, we learned that R was 0.08206. Is that just rounded? Is that the one you want us to use?
Yeah.
Will it make a difference if we use the 0.08206?
Shouldn't be much of a difference, but typically I require my students to use 0.0821.
Okay, thank you.
All right. Okay, so let me clear this. Get rid of that. Scroll down to the next question. And the next question now deals with, okay, the next question deals with situations where you have a system which is not at equilibrium and you're asked to predict which direction the reaction will proceed in order to achieve equilibrium. All right. So let me just do a little discussion of this here just to, give you some idea as to what this is talking about. So let me go to this right here. So let's say you have a system A going to B, all right? And if it's at equilibrium, Kc would be the constant value, whatever that is, right? Now, let's say the system is not at equilibrium, all right? Then we can still have the relationship between A and B, where the concentration of B would be on the numerator side, which is a product, and the concentration of A would be the denominator. But because this system is at this instant not at equilibrium, that means that we cannot put Kc being equal to this, right? So therefore, there's a term that we use called the reaction quotient, which is symbolized by this right here, Qc. So Qc is the reaction quotient, right? And the reaction quotient is not a constant. All right? So, because the system is not at equilibrium, the system will try to find its equilibrium state. Now, it depends on the value of Qc relative to Kc, right? So here are the different scenarios here. If Qc is greater than Kc, then the reaction shift will be to the left in order to, I'm sorry?
It goes towards the reactants.
Exactly, towards the reactants, exactly, to the left, right? So the reactants are on the left, the products are on the right. So if Qc is greater than Kc, the reaction shift will be towards the left, which would be towards reactants. If Qc is less than Kc, then the reaction shift would be to the right, okay, towards the product. All right. And finally, if QC is equal to KC, then the reaction system would be at equilibrium, all right? So basically, when you're given a question where you're given some numbers representing the concentration of the different components in the system, right? And you're asked to find out which direction the reaction will shift in order to achieve equilibrium. Basically, what you need to do is calculate QC and compare it to the given KC value. If QC is greater than KC, then the reaction will shift to the left, favoring the formation of reactants, all right? And then equilibrium will be achieved. If QC is less than KC, then the reaction will shift to the right, favoring the formation of products. And then the system eventually will end up in an equilibrium state, all right? So that's basically what you're going to need in order to answer question number 4, all right? So question number 4 says that at 500 degrees Celsius, the equilibrium constant for the following reaction is 0.080. So basically, they gave you the KC value right here. So I'm just going to write down KC for that system. Then it says, given the concentration of ammonia is that, the concentration of nitrogen is that, and the concentration of hydrogen is that, find Q. Q here in this case would be QC, right? And then predict how the reaction will proceed, all right? So first thing I'll do is write down the expression for QC based on this equation here, and that would be equal to the concentration of NH3 squared divided by concentration of N2 times the concentration of H2 cubed. And then I'll put in the values. First, the for ammonia, which is 0.0596, and then I'll square that, divided by the concentration of nitrogen, which is 0.600, multiplied by the concentration of H2, which is 0.420, but this now would be cubed. And then I would do the number crunching, which I already did. Let me see if I can bring it up here. So when I did that, the answer I got is 0.99. I'm sorry, 0.0799. So this is QC, right? And when I compare QC to KC, you'll notice that QC is slightly less than KC. So I'm just going to say here that QC is less than KC, right? So what does that mean? It means that the reaction will shift
To the right.
slightly to the right. All right, in order to achieve equilibrium. Right. All right. So that's basically what we can conclude based on what we just did. All right. Any questions about this?
So if it's less than 1, it's always going to shift to the reactants or
If
to the
it's
right, I
less-
mean, the products.
If it's less than KC, if QC is less than KC, then yes,
Okay.
it will shift to the right in order to, basically when it shifts to the right, what happens? The concentration of the products would increase, the concentration of the reactants will decrease, the KC would increase until it gets to the KC value. You see what I'm saying? So that's what's going to happen if at a certain instance, a QC is less than KC. And then the opposite will happen if it's reversed. If QC is less than KC, or if QC is greater than KC, then the reaction is going to shift to the left in order to reduce QC so that it becomes equal to the KC value. All right. Okay, any other questions about this? Any other questions? Any other questions? Okay, so let me clear this. And let me scroll down. Now, if you understood what I did in number 4, then you should be able to do or you should be able to tell me what to write down for number 5, all right? So in the case of number 5, they gave you the Kc value, and they gave you the concentrations of the different components in this mixture. So the question is asking for you to calculate Q, all right, and determine how the reaction will proceed. So the expression for Q would be equal to what?
Concentration H2
Okay, very good.
times
Mhm.
concentration CO2
Okay. And then
over concentration CO
the-
times concentration H2O.
Okay. So we put in the numbers, right? So for H2, it is 0.42. For CO2, it would be 0.37. And for carbon monoxide, it is 0.15 times for H2O, which is, where's H2O? 0.25, okay. So when I did that calculation, this is what I got. I got 4.1, right? So this is QC, and this is KC. So what do we notice? This is KC right here, right? KC. So what do we notice when we compare QC to KC?
QC is smaller than KC.
Okay, so if QC is less than KC, which direction will the reaction shift?
To the reactants.
Nope.
I mean, to the products.
Exactly, because you want to increase QC. So therefore, reaction will shift to the product side or to the right. All right. And that's basically how that is done. Okay. Any questions about that one? Any questions?
Yes.
Mhm.
Go ahead.
Sorry, I noticed that most of the answers or the givens have the M after that. Is it important to write the units in the equation? Does that make a difference or?
Okay, so as I said before, when it comes to the Kc value, the common practice now is that we don't need to include the units. So basically, it doesn't matter if you put the units for M in your calculation. So like, for example, in the case of this case, you'll notice I did not put any M's, any units for the molarities. And that's because you're not concerned with the units of Kc or Kp or whatever in the final answer. All right, so you can put the M's if you want to, but it's not necessary. Not in this case. Generally speaking, it would be necessary, like, for example, what we did in the previous 2 chapters. But in this case, as I said before, the standard practice now is that for KC or QC for that matter, we do not include the units. And I won't go into the reason why. There's a reason why nowadays they don't do that. Like I said, when I was in school, we had to be particular about the units, even in these situations. But for some reason, well, I know the reason why actually, but I won't go into it right now. They have stopped requiring that, you know, you include the units for KC or KP or QC, whatever. Okay.
I have a question.
Yes, ma'am.
So I noticed on the last problem, you put that the reaction shifts slightly to the right because it was a lot closer.
Exactly.
Where's the cutoff for saying that it's slightly to the right or just will shift to the right?
The cutoff would be when it's equal, exactly equal. If the KC is equal to QC, then basically there'll be no shift to the right or left. It will be at equilibrium.
Sorry, I think I just meant, like, what does the difference need to be to say that it's slightly to the right versus just to the right?
Well, if there's any slight difference, like in this case here, let me scroll back up here. Hold on. Shoot, hold on. In this case here, the KC was what, 0.0799, right?
Yeah.
So I mean admittedly it's a small difference.
So like if
but
the
like-
answer was 0.75, would you still say slightly?
Yes, exactly. As long as there's a difference between that and that. Now, if the answer was 0.0800, then basically there'll be no shifting, because this is exactly equal to the KC value. As long as there's a difference between KC and QC, a numerical difference, there will always be a shift either to the right or to the left, depending on whether or not QC is greater than KC.
Okay, and if there was a question on a test where it was slightly and we didn't put slightly, would you count points off?
No, I just basically put slightly to emphasize, that it would be a very small shift. All right. Okay, so I hope that answers your questions. Okay, so let me clear this. Do this, scroll down, and let's talk about Le Chatelier's principle, which is what this number 6 is all about. Okay, so if you watch the videos, you know that I spent a lot of time talking about Le Chatelier's principle. And let me just apologize to anybody in this class who speaks French, because I know I've just massacred that famous chemist's name. Let me spell it out for you. It's I think it's pronounced Le Chatelier's principle, right? And, I've been pronouncing it Le Chatelier's for all this time that I'm simply too lazy to pronounce it properly. Anyway, so what this principle is about, it's about what would happen if you make a change to a system already in equilibrium and how the system will respond to the change, right? And basically what this principle says is that if you have a system already at equilibrium and then you change one factor, right? Then the system will respond in such a way so as to counteract your change. And the reason why that happens is because when you make a change in one factor, you're disturbing the equilibrium. The system will try to regain equilibrium by doing the opposite of the change that you imposed, all right? So for example, let's say you already have a system in equilibrium, and let's say that you suddenly increase the concentration of one of the components in a mixture. Then what the system will try to do is decrease the concentration in order to reestablish equilibrium. And the system will behave in a certain way in order for you to, in order for the system to achieve equilibrium, all right? And in the video lectures, I covered 4 factors. One is concentration. The second one is the pressure. And this is for gaseous systems. So let me just put in parentheses here, gaseous systems. The third factor that we look at when it comes to Le Chatelier's principle is temperature. And the fourth and final and easiest factor to look at is the presence of a catalyst, all right? So these are the 4 factors that was looked at when it comes to predicting how a system will respond when it comes to changes in any of these when the system is already at equilibrium, all right? So let me just quickly describe what happens when you change the concentration of one component in a system. Now, remember, the thing that we look to in order to make these predictions would be Le Chatelier's principle, right? And as I said before, Le Chatelier's principle says that whatever change you make to a system, the system will respond by counteracting that change in order to reestablish equilibrium. So in the case of concentration, we're going to see how changes in concentration will affect the equilibrium of a system. And the example we're going to look at here is SO3 gas plus O3, I'm sorry, O2 gas. Oh, my bad. This should be SO2 gas right here. So this should be SO2 plus O2 gas in equilibrium with SO3 gas, all right? So this is a system already in equilibrium. So let's look at increasing the concentration of O2, all right? So that is a change imposed. So let me put here change imposed, right? So according to Le Chatelier's principle, if this is a change imposed, then the system will respond by decreasing the concentration of O2, all right? And this should be O2 here. Let me erase this here. Okay, so the question now becomes, how will the system decrease the concentration of O2 in response to increasing the concentration of O2? What's going on here?
Will it shift to the right?
Hold on 1 minute. Oh, okay. I was just trying to choose the right pen to write with. Okay, so somebody was saying shift to the right. Now, that would be indeed correct, because by shifting to the right, some of the O2 will react with some of the SO2, and the amount of SO3 would increase, right? So therefore, system, let me write it here, system will shift to the right, and therefore, in addition to the concentration of O2 decreasing, the concentration of SO2 will also decrease, and the concentration of SO3 will increase. All right? So that's basically how the system will respond when you when you increase the concentration of O2. So just to recap, the change you're imposing is that you are increasing the concentration of O2. According to Le Chatelier's principle, the system will respond by doing the opposite of what you're trying to do, right? So you're increasing the concentration of O2. The system will respond by decreasing the concentration of O2. And the way the system will achieve that in this particular case is that the system will shift from left to right, all right? So therefore, it will favor the formation of SO3, but the concentrations of O2 and SO2 will decrease. And by the way, I forgot to balance this equation here, so let me do that now before I forget. This should be a 2 here, and this should be a 2 here. That's important for what we're going to discuss later on, all right? Okay, any questions about what I just said? Any questions? Any questions? Any questions about how the system responds when you increase the concentration of O2? Okay, so we're going to work with this equation here, but this time, let me just erase this bottom part right here. This is going to look messy. So I apologize for that. Okay, so let's see if you understood what I was saying. I'm going to use another possibility. So let's say that the change I'm imposing is that I am, why does it happen? Okay, so let's say that the change I'm imposing, change imposed, is that I am decreasing the concentration of SO3. Okay, so that's a change that I am imposing. I'm trying to find, hold on. Okay, this thing switched on me. Anyway, so the change I'm imposing is that I am decreasing the concentration of SO3. So my question to you is, how will the system respond if I'm trying to decrease the concentration of SO3, right? How will the system respond? System will respond by doing what?
Increasing the concentration of SO3.
Exactly, increasing the concentration of SO3. So how would that be achieved? How will the system increase the concentration of SO3? In other words, which direction favors the formation of SO3? Anybody? Which direction shift will favor the formation of SO3? Would it be to the right or be to the left? Anybody? Hello? This should be easy, folks.
Is it to the right?
Exactly. So the reaction, right, is here, will shift to the right. So what that means is that the concentration of SO3, of course, would increase as a result, and the concentration of SO2 and O2 will decrease. All right. And that's it. That's basically how the concentration of one, just changing the concentration of one component in a mixture, how it changes the equilibrium shift. So just to recap, when it comes to concentration, if you change the concentration, and it doesn't matter if you're increasing or decreasing, whatever change you're imposing, the system will do the opposite, right? And the system will shift accordingly in order to oppose the change that you impose, all right? So if you increase the concentration of something, then the system will try to decrease the concentration of that thing and will shift away from that substance in the balanced equation. And the opposite will be true if you try to increase the concentration or decrease the concentration of that same item, all right? Okay, so that's basically as far as concentration is concerned. Now, let me get rid of this here, and let's look at another factor, which is pressure. That's the second factor. Now, when it comes to pressure, there are two parts to this discussion, right? I'm going to label them A and B, right? Now, in the case of A, we're going to look at what happens when you change the pressure of one component. So I'm just going to put one component, which is a gas, right? And then we're going to look at changing the total pressure of the entire system, right? So basically, there are two aspects we're going to look at here, and we're going to look at each in turn, all right? And I'm going to go back to the same example that we had before, all right? And this is where you're going to see, at least for the B part, you're going to see why it's important for you to have a balanced equation in this case, right? So I keep putting 3 here. There should be 2. Should have a 2 here and a 2 here, all right? And these are all gases. So what I'm discussing here relates to gaseous systems, such as this example right here. Okay, so let's look at the A part, right? So as an example, well, before we get to the examples, so let me remind you again of what Le Chatelier's principle says. Whatever change you impose on the system will respond by doing the opposite and will shift accordingly, right? Whatever change you impose on the system will respond by counteracting the change that you impose, all right? So in the case of this part here, I'm going to say, let's say we increase the pressure of SO2, right? So the question is, how will the system respond? Well, the system will respond by decreasing the pressure. So in fact, let me make this a bit more orderly. Let me just erase this here. And let me go back to this. So let me just follow the same pattern I've been doing. The change that you're imposed, is that you are increasing the concentration of SO3, all right? Not pressure, concentration. Let me erase this here. Or not concentration, pressure, that's what I meant to say. Okay, so we're increasing the pressure of SO3, all right? So the question is, how will the system respond? System will respond by decreasing the pressure of SO3. Now, here's the thing. The pressure of any gas is directly proportional to the concentration of that same gas, right? So basically, whatever you do to the pressure, you're doing to the concentration, right? And that is no less true for the sulfur trioxide. So basically, we can say that system will respond by decreasing the pressure of SO3, which means that the system will also respond by decreasing the concentration of SO3. Now, based on what we said earlier, if the concentration of SO3 is decreased, how will the system respond? Anybody? If you decrease the concentration of SO3, which direction will the system shift in order to, if you increase the concentration, well, if the concentration of SO3 is decreasing, how will the system do that? That's a better question to ask.
By shifting to the left.
Exactly. So therefore, system will shift to the left, right? So if it shifts to the left, what happens to the concentration of SO2? The concentration of SO2 will what?
Increase.
Exactly. The concentration of O2 will?
Increase.
And the concentration of SO3 will?
Go down.
Exactly. Right? So basically, the argument that you'd follow, or the logical sequence of the logical sequence that you'd follow for pressure of one component changing is basically the same thing for concentration. All right. So if you understood what we discussed earlier with respect to changes in concentration, then it's basically the same thing for changes in pressure for one component. All right. So that part is, you know, kind of straightforward based on what we understood before. All right. Okay. Before I erase this, are there any questions about this? I want to make sure that you understand this before I move on. Any questions? Any questions? Okay, so let me eliminate this here. And now we're going to look at what happens when you change the total pressure, right? So this is the B part of the two-part discussion regarding pressure changes. So here we're going to look at change in total pressure. All right. Now, again, we're going to go straight back to the same example. 2 SO2 gas plus O2 gas to give 2 SO3 gas. All right. So, question is, okay, what if we change the total pressure? So, change imposed. Let's say the change imposed is that we're going to increase total pressure. All right. So that's the change we're imposing. So the question is, how will the system respond? Now, again, we have to go back to Le Chatelier's principle, which says that whatever change you impose on the system will respond by opposing that change that you're imposing. So if you're increasing total pressure of the system, based on Le Chatelier's principle, how will the system respond? System will do what?
Decrease the total pressure.
Will decrease total pressure. So the question now becomes, how will that be achieved in this case? The key to answering that question is looking at the total number of moles represented on both sides of this equation here, right? And this underscores the importance of having a balanced equation. So if you look at this equation here, you'll notice that you have 2 plus 1 moles of gases. So you have a total of 3 moles of gases on the left side. And on the right side, you have only 2 moles of gases present on that side, right? So in order to answer the question, which direction the reaction will shift in order to decrease the total pressure, the direction shift will be from the side with the higher number of moles to the side with the lower number of moles. Because when you have that shift, the number of moles of gases will decrease, and therefore the total pressure will decrease. So therefore, system will shift to the side that has fewer moles of gas. All right. So therefore, in this case, what it means is that it's going to shift to the right. All right. So if it shifts to the right, what happens to the concentration of SO2? Anybody? If the reaction shifts to the right in order to achieve equilibrium, what happens to the concentration of SO2?
Decreases.
I'm sorry?
It decreases.
Exactly. And what happens to the concentration of O2?
It also decreases.
Very good. And what happens to the concentration of SO3?
It increases.
Very good. Exactly. So that's basically what happens when, if it's a totally gaseous system, what happens when you change the total pressure, right? In this case, we're talking about the increase in total pressure. If you were to decrease the total pressure, then the shift would be in the opposite direction, okay? So in this particular case, if you increase the total pressure, the system will respond by doing the opposite. The system will try to decrease the total pressure. And in this case, what you do is look at the total number of molecules represented on both sides of the equation, right? So in this particular case, because the system will decrease the total pressure, in response to the change imposed, the system will shift from the side which has a greater number of molecules to the side which has the lesser number of molecules. So in other words, it's going to shift to the right. And therefore, as a result of that, the concentration of SO2 and O2 will decrease, and the concentration of SO3 will increase. All right? Okay, any questions about this particular example? Any questions? Any questions? Okay. So let me ask you this question. See if you understood what we just covered. Suppose you're given H2 gas plus I2 gas to give HI gas. And let's say you're increasing total pressure. So my question to you is, which direction will the system shift to? Will it shift from left to right or from right to left?
Would it be from,
Oh, I'm sorry. Again, I forgot to balance the equation. You need a 2 here. That's important. Okay, so question still stands. Which direction will the reaction shift in response to increasing the total pressure?
don't they have the same amount of moles on both sides?
Okay, so what does that mean?
So maybe it won't shift?
Exactly. Right? If you have equal, I'm sorry?
Does it mean they're in equilibrium?
Well, it's already in equilibrium, but the equilibrium position will not shift because as the young lady, I don't remember, I don't know who that was, but as the young lady said, they have equal number of molecules on both sides. So therefore, there's no net shift in the direction left to right or right to left if you change the pressure. So it doesn't matter if you increase the total pressure or decrease the total pressure, there'll be no equilibrium shift, right? So therefore, the concentrations will not change. All right. So I just thought I should throw that one in so that I am satisfied that you understand how this works. Okay, the very last factor we're going to look at is addition of a catalyst. Addition of a catalyst. Now, in this particular case, this is the easiest of the factors to understand, right? And the reason why is that when you add a catalyst, when a catalyst is added, the rate of the forward reaction and reverse reaction will increase to the same extent. All right. And if you remember what we talked about in the previous chapter, the chapter before this one, what the catalyst does is that it basically lowers the activation energy of the reaction. And the thing is, it lowers the activation energy for both the forward and the reverse reaction. So the result of that is, therefore, the result is no equilibrium shift one way or the other. All right. There'll be no shifting of the equilibrium position to the left or right. Basically, both reactions will just simply proceed at a faster rate, but the concentrations of the different components would still remain the same. All right. So that's basically what happens when a catalyst is added to a system which is already in equilibrium. All right. So that's the easiest one. That's pretty much all we can say about that. All right. Okay. So with that out of the way, now I feel that we're in a position to answer question number 6. But we're going to take a break first. All right. So we're going to get back together at 12 o'clock. And then the first thing we're going to do is look at question number 6. All right. Okay, I am back. So now that I've covered what I just covered before the break, we should now be able to do question number 6. All right, so question number 6 says, state and explain the changes in equilibrium position for the reaction, and it gives you the balanced equation. And then that would, it continues to say that will occur at constant temperature if, and it gives you some, possibilities. The first of which is if the pressure or concentration of nitrogen increase. All right, so what they're saying is that you are increasing the concentration of nitrogen. So that will increase. So the question is, you're to state what change will take place. Basically what they're asking for is the direction of the shift. That's the first part. So let me hear your answer. What do you think the answer is as far as the shift is concerned? Will the reaction shift to the left or shift to the right?
Right.
Okay, so shift to the right. So what's going to happen to the concentrations? Let's start off with the nitrogen. Will that increase or decrease?
Decrease.
I'm sorry?
It will decrease.
Yes, you're indeed correct. So the concentration of nitrogen will decrease. What about the concentration of the oxygen?
Also decrease.
And what about the concentration of the NO?
Increase.
Exactly. So that's basically the answer for the A part. All right. Okay. Any questions about this one? Any questions?
Yes, at this level here, does the coefficient in front of the NO matter when you're
No.
writing this stuff in?
Not for this part.
Okay,
It only matters if the total pressure changes, right? Okay.
okay,
Mhm.
thank you.
Okay, any other questions before we move on? Any other questions? All right, so let me get rid of this here. And I just remembered something. There's something I forgot to mention in the last discussion before the break, but I'll get to it. Let's just continue this question, and then I'll get to what I forgot to mention. Okay. In this case, it's talking about changing, or I should say, increasing the pressure or concentration of NO. Now remember, the equation for this reaction is N2 plus O2, N2 gas plus O2 gas to give 2NO gas. And this is an equilibrium. Okay, so in this case now, you are increasing the concentration of NO, right? So how will the system respond? Or will it shift to the left or should shift to the right? Equilibrium shifts to what? If you increase the concentration of this, which direction will the reaction shift?
To the left.
Okay. And then what does that mean for the concentration of N2? Will that increase or decrease?
Increases.
What about the concentration of O2?
Also increases.
And what about the concentration of NO? I'm sorry.
Decreases.
Exactly. Okay. So that's the B part. Okay, now the C part says the total pressure of the system is increased. So you're increasing the total pressure of the system. So remember what we said you look for when you're looking at the total pressure. What are we looking at?
The moles?
Okay, so we're looking at the moles of gases on each side. So what's the total number of moles on the left side here?
2.
And what's the total number of moles on the right side?
2.
Okay, good. So what would be the effect of increasing the total pressure?
There would be no change.
No change, exactly. All right. So therefore, there'll be no increase or decrease in any of the components in the system. Okay. And then what about D? The total volume of the system is increased, right? So what do you think is going to happen in that case? Well, let me give you a hint. If you have a gas or gases in a container and you increase the total volume, what effect does that have on the total pressure?
Decreases it.
I'm sorry?
If you increase the total volume of the system, it'll decrease the pressure.
Okay, good, very good. So when you increase the total volume, the total pressure decreases. So what do you think is going to happen in this particular case? Will the system shift in either direction?
No.
Exactly, because of what we said before in the case of C. You have 2 moles of gases on either side. So even changing the total volume will not change the total pressure. Well, you'll change the total pressure, but that will not change the equilibrium position because you have equal number of molecules on both sides of the equation. Okay, so the answer for D would be the same as the answer for C. Okay, so for E, let me clear this first and then do
Quick
this.
question.
Yes, ma'am.
When you decrease the total pressure, it starts shifting towards the side with the fewer moles. If the systems are
It shifts to the side with a greater number of molecules. If you decrease the total pressure, remember the Chandler's principle says that the system will try to increase the total pressure, which means that the equilibrium position will shift in the direction favoring greater number of gas molecules.
Okay, thank you.
All right. Okay. Scrolling down, when you add a catalyst, what did we say about adding a catalyst? What effect will it have on the equilibrium position?
The result is no equilibrium shift.
Exactly. And the reason why, if you recall, is that you're speeding the rate of both the forward and reverse reaction pretty much to the same extent. So therefore, the back and forth will increase in terms of the rates, but the amounts of each of them will still remain the same. All right. Okay. And then we get to F. If you decrease the concentration of O2, right? So let me remind you of the equation again. It is N2 gas plus O2 gas to give 2NO gas. All right. So what if you all of a sudden decrease the concentration of O2, right? Which direction will the reaction shift? Shift to the what? To the left or to the right?
The left
Exactly. So what does that mean for the concentration of N2?
increases.
What happens to the concentration of O2?
Increases.
And the concentration of NO would?
Decrease.
Exactly. Okay, very good. All right, so that's basically how that is done. All right. Any questions about this? Any questions? Any questions? Okay, so let me clear this here and scroll down to question number 7. And in question number 7, now we're going to get into more quantitative aspects of equilibrium, all right? So it gives you the balanced equation for this reaction, and it says, in a study of hydrogen halide decomposition, a researcher fills an evacuated 2.00 liter flask with 0.200 moles of hydrogen iodide gas, allows the reaction to proceed at 453 degrees Celsius. And then the question says, at equilibrium, the concentration of HI is 0.078 m. And the question is asking for you to calculate Kc. Now, in this type of question, where you're given amounts of a particular component in a system before equilibrium, and you get a value at equilibrium, the best way to approach a problem like this is to set up what is called an ice table, all right? And let me just show you what we mean by that. So basically, the first thing I would do in answering this question is that I'll try to find the initial concentration of hydrogen iodide. So let me do this here. So the initial concentration of hydrogen iodide, that would be equal to the moles of the hydrogen iodide, which is given here. So that would be 0.200 moles. And I would divide it by the volume, which is given here. So that's 2.00 liters. And I would work that out. And when I did that, I got 0.100 M, all right? So I'm just going to rewrite this equation right here. In fact, let me scroll down. Okay. Okay, so let me, okay, what am I going to do? Let me, okay, I want to make sure that you have written this down. So let me know when you have done that, because I want to create some space right here.
I have it written down.
Okay, I'll assume that to be the case for everybody else. Okay, so let me clear this here. So what I'm going to do now is set up what is called an ice table. What I'm going to do first is rewrite the original equation down here, which is 2HI gas to form H2 gas plus I2 gas, right? And initially, well, the I stands for initial, change, and equilibrium. All right. So let me just draw some lines here to make the separation more pronounced. Okay. And the first thing I'm going to write down in this table is what is given here. It says here at equilibrium, the concentration of hydrogen iodide is 0.078. So that means right here in this spot, I'm going to write down 0.078 M. Now, the initial concentration of HI is what I calculated earlier, which I erased, but that answer or that value is 0.100 M, all right? So initially, you had this amount of HI, you had 0 H2 and 0 I2 present, right? At equilibrium, the concentration of HI falls from 0.100 M to 0.078 M. So we can figure out what the difference is, and that difference would be the change that I'm going to write down here. So basically what I'm going to do is find the difference between 0.100 M and 0.078 M. And according to my calculation, that change is going to be minus 0.022 M, all right? So that's a change as far as the hydrogen iodide is concerned. Now, based on that change and based on the stoichiometry of the equation, we can find out the changes in the concentration of both hydrogen and iodine. How do we do that? Well, since we know that this represents the amount of HI that reacted, and there's a 2-to-1 ratio between the HI and the H2, we can say, therefore, that the change in the concentration of H2 would be plus a half of this value, right? Because for every 2 moles of HI that reacts, 1 mole of H2 is produced. So right here, I'm going to put half of 0.022, which would be 0.011, and that will be positive. And because we have a 1-to-1 ratio between the iodine and the hydrogen, the change in the concentration would also be, for iodine, 0.011 M. So at equilibrium, the concentration of H2 would be 0 plus this value, which works out to be 0.011 m. And the same would be true for the iodine, 0.011 m. All right. So now we have the last line in this table completed. And each of these values represent the concentration of each of these components in that mixture. So now we can write down the expression for Kc, which is, as you may recall, would be the concentration of the products. In this case, it would be hydrogen and iodine, and then we divide it by the concentration of Hi squared, and then we put the numbers in. So the numbers that we're going to put in is 0.011 m multiplied by 0.011 m divided by 0.078 m squared, and then we work that out, and according to my calculations, this works out to be equal to 2.0 times 10 to the minus 2, and that would be the value of Kc for this system. All right. Okay. Any questions about this particular problem? Any questions? Okay. Is it okay for me to clear this? Okay, so let me do that right now. And let's move on to question number 8. Now, in the case of question number 8, they gave you a balance equation, and they gave you, it's a totally gaseous system, and they gave you the pressure of each gas, they gave you the volume, and they gave you the Kp value, right? So the first question that is asked is this above system at equilibrium? And you're to explain. Now, if you remember, when it comes to determining whether or not a system is at equilibrium, what we do is that we calculate the QC, or in this case, the QP for the reaction, which is the reaction quotient, and we compare it to Kc or Kp, all right? We're dealing with Kp in this example. Okay, so first thing I would do, let me just scroll down a bit here, is that I would determine or calculate QP. So QP is equal to pressure of SO2 times pressure of Cl2, all divided by pressure of SO2 Cl2. And we put the numbers in. So according to the question, the pressure of SO2 is 0.30 atmospheres multiplied by the pressure of chlorine, which is 0.16 atmospheres, divided by the pressure of SO2 Cl2, which according to the question is 0.50 atmospheres. And according to my calculations, this works out to be equal to 9.6 times 10 to the minus 2, all right? Now, because this is not equal to the Kp value, which is equal to 0.011, what this tells me is that the system is not at equilibrium. All right. So once we calculate QP, we see if it's equal to Kp. If it's not, then we know that the system is not at equilibrium. All right. Okay. Any questions about that? Any questions? Any questions? All right. Is it okay for me to clear this? Is it okay for me to clear this?
Yes.
Okay, all right, so clear it I shall. Let me scroll down here. So the next question is, if the system is not at equilibrium, which it isn't, in which direction will the system move to equilibrium? Now, in order for us to answer that question, again, we have to compare QP to KP. And the QP we calculated was 9.6. Oh Lord, let me do this again now. The QP that we calculated was 9.6 times 10 to the minus 2, right? And the KC value is 0.011, right? So which one would be greater? QP is equal to 9.6 times 10 to the minus 2, which is equal to 0.096, while KP is equal to 0.011. So that tells me that QP is greater than KP. So which direction will the reaction shift?
To the left.
To the left. So therefore reaction will shift. Shift to the left. And this answer here will become important in order for us to answer question number C, or question C, I should say. All right, because question C says, what will be the concentration of SO2 when the system achieves equilibrium? All right, okay, can I clear this?
Yes.
All right, let me do that. Let me scroll down. Okay, so the question is asking, what will be the concentration of SO2, CO2 when the system achieves equilibrium? So what I'm going to do here is rewrite the same equation here and set up an ICE table, kind of similar to the one that we did for the previous question. So the equation is SO2, CO2 to form SO2 plus CO2, right? Now, initially, based on the information provided in the question, the pressure of SO2 will be 0.50 atmospheres. The pressure of SO2 would be 0.30 atmospheres. And the pressure of the chlorine is going to be 0.16 atmospheres, all right? Now, because the question we answered earlier in the C part, remember we said that the reaction is going to shift to the left, right? What that means is that some of the SO2, because it's going to shift to the left from the right, that means that some of the SO2 will react with some of the CO2 to form SO2-Cl2. Now, we don't know what that amount is. In fact, we need to find that out. And the way to do that is to basically say that X represents the amount of SO2 reacting, all right? So if X represents that, that means that as far as the SO2 is concerned, the change for the SO2, let me draw a line here, the change for the pressure of SO2 will be minus X, and because there's a 1-to-1 ratio between SO2 and Cl2, this would also be minus X, and because there's a 1-to-1 ratio also between the SO2 and the SO2-Cl2, that would be plus X, because the reaction is shifting in the direction of the SO2-Cl2. So that's a change in the pressure for SO2-Cl2. So we can write down different expressions for the different components at equilibrium. In the case of SO2, at equilibrium, the pressure would be 0.50 atmospheres plus X. For the SO2-Cl2, that would be 0.30 atmospheres minus X. And for the Cl2, that would be 0.16 atmospheres minus X. All right. So next step is we're going to write down the KP expression. And I'm going to in the interest of spacing, I'm going to put that over here. So in fact, let me continue down here. So Kp is going to be equal to, based on the equation, the pressure of SO2 times the pressure of Cl2 divided by the pressure of SO2 Cl2. And then we're going to put each of these terms into their respective positions here in this expression. So for SO2, that's 0.30 minus X multiplied by the pressure of Cl2, which is 0.16 minus X. And then down here, I'm going to have 0.50 plus X, and that would be equal to Kp, which is equal to, according to the question, 0.011. Okay, and basically, you need to go through several algebraic steps, which I won't go into right now. I'm just going to get to the equation that you need to solve. And that equation will be x squared minus 0.047 x plus 0.043 equals to 0, all right? So I'm jumping quite a few steps in order to get from here to here, right? And you'll notice that this equation here is actually a quadratic equation, all right? And therefore you can use a quadratic formula to solve that. Just to remind you what the quadratic formula is, it is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Or, and I'm a very kind person when it comes to this, what you can do, instead of using the quadratic formula, you can actually use your fancy calculators. I know that some of you have calculators that are programmable. I will allow you to use that. If you don't know how to program it to solve a quadratic equation, please find out how to do that. In fact, if I'm not mistaken, I have posted a video. Let me see if I can find it here. Let me get out of, let me see here. Where shall I go? Let me go to here. Let me close this. If you go to announcements, if I remember correctly, and okay, so this is where, I don't know if you can see it behind the writings, but right here, program TI-83/84 calculated to solve quadratic formula. I've posted a YouTube video. Please go there and watch it because they go into the steps as to how you can program your calculator if you have that type of calculator. And you can basically, after programming it, all you have to do is enter the A value, the B value, and the C value. And your calculator will basically show the two solutions that would be the answer of that problem, all right? So that's basically what you're going to need to do. So I would strongly recommend that you do that in preparation for your future exams, all right, or future tests. Okay, so back to the problem at hand. Okay, so back to the problem. So now that we have the quadratic formula, then you can, or quadratic equation, you can solve for x. And again, I won't be going through all the steps to show you how to determine x. As I said before, you can use your TI-83, TI-84 to do that. All I'm going to do here is show you the two x values that would be the solution to this problem. So one x value is equal to 0.35, and the other x value is equal to 0.12. Now, the thing is, only one of these values would be valid. And in order for us to figure out which one it is, all we have to do is look at here and here. Because obviously, whatever the x value is, that x value here must be less than these two numbers, because you're subtracting x from each of these, and you cannot have a negative pressure. The pressure must be positive, which means that X must be less than 0.16 and 0.30. So the answer here is that X must be equal to this, right? Because between these two numbers, this number here is less than 0.16. Okay, so now that we have established what X is, we can find out what the pressure of SO2 is, because remember now the question is asking for the concentration of SO2-Cl2. So you can find out what the pressure of SO2-Cl2 is. That would be equal to, based on this right here, 0.50 atmospheres plus 0.12 atmospheres, which would be equal to 0.62 atmospheres. So to find the concentration of SO2-Cl2, that would be equal to the pressure of SO2-Cl2 divided by RT. All right? And I'm running out of space, so let me just continue up here. So that means that the concentration of SO2-Cl2 is equal to the pressure of SO2-Cl2, which is 0.62 atmospheres, divided by R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is, according to the question, 300 Kelvin. And that's it. You work that out. And according to my calculations, that works out to be equal to 0.025 M. So this would be the answer right there. And that's basically how that is done. All right. Okay, any questions about this? Any questions? I will admit this is a bit lengthy, but this is just basically the nature of these kind of problems. All right. Okay, any questions about this one? Any questions? Any questions? Okay.
I have a question.
Yes, ma'am.
When you get to the PSO2Cl equals 0.50 plus 0.012, where did that come from?
That comes from right here. Because this represents the pressure at equilibrium.
Right.
And we solve for X. And the X is
Oh,
0.12.
okay.
So we
Okay.
add that to the 0.5, which is what we did right here.
Okay.
All right. Okay, any other questions? Any other questions about this one? Any other questions? Any other questions? Okay, so is it okay for me to clear this? Are you finished with writing this off? All right, so going once, going twice. Okay, let me clear this. And let me do this. And let me scroll down. And I think this is the last question, if I'm not mistaken. Let me just check something here. Yes, indeed, this is the last question. All right. So the question says, you're to calculate the concentration of these three components that are present in the following gas phase reaction that comes to equilibrium at 450 degrees. I'm sorry, 450 Kelvin. It gives you the Kc value and it gives you the initial amounts of each of these components, all right? Okay, so based on what we covered in the last question, you should be able to at least make a start on this one. So my question to you is, what would be the first step in this process?
To be honest, I'm extremely lost and still taking in all the information from the last question.
Okay, I can appreciate that. If you have any questions concerning what we just covered, even though I erased all of that stuff, feel free to talk to me. If not now, during office hours. Man, this rain is falling real hard. Dang. Okay, so they gave you the initial amounts, right? They gave you the KC value, okay? And the question is asking for, let me just do this here. The question is asking for the concentrations of PCl5, PCl3, and Cl2. So let me give you a start here. What the question is asking for are the equilibrium concentrations, right? They gave you the initial concentration. And if you remember, I talked about using what we call the ice table. So remember, the ice table stands for ice, initial, change, and equilibrium. Oops. All right. So they gave you the initial amounts, and it says that, hold on. The question says calculate the concentrations of everything at equilibrium. So the question is asking for you to calculate these values here, here, and here, right? Let me draw a line here. Draw a line here. Okay, so basically what we need to do is find the changes here. So what I'm going to do here is say let X equal to concentration of PCl5 reacting. All right. So that means that the change here for the PCl5 would be minus X. So what do you think the changes for PCl3 and Cl2 would be? If the change here is minus X, and this is a 1:1:1 ratio, what would be the
Plus
change?
X.
Exactly, plus X, right? And what would be the change for chlorine?
Plus X.
Plus X as
Plus
well.
X. Okay, good. So how would you complete this last line? Let me erase the question signs here. Okay, so how would you, whoops, go back to this. How would, hold on. Okay, so how would you complete this line here? All you have to do is add these up.
1.00 minus X.
1.00 minus X. X plus 0 gives you X. X plus 0 gives you X, right? So if you were to write down the Kc expression, Kc is equal to concentration of PCl3 times the concentration of Cl2, all divided by the concentration of PCl5. And then we put the terms in. So PCl3 and Cl2 would be the same. That's X times X. That would give you X squared over 1.0 minus X. And we can set that to be equal to the value of Kc, which is given right here, which is 0.0013, all right? So this is basically what we have to solve. We have to solve for X, all right? And again, as I said before, for the previous example, I won't be showing you all the steps. It's a lot of algebra involved. You should be able to work that out. What I'm going to do is show you the final, well, not the final, but the resulting quadratic equation, all right? So is it okay for me to clear this? Because I'm going to need some space here.
Yes.
Okay, I'll take your word. I'll take it that you represent everybody. So let me clear this right here. So I'm just going to write down the equation that I ended up with, which is X squared plus 0.0013 X minus 0.0013. And that would be equal to 0, all right? Now, I need to do something here. Give me 1 minute because I don't think what I have here is correct. I must apologize for this. So let me, okay, so Okay. Okay, so there are two possible answers in this case. One of them would be for X. One of them would be 0.035, and the other one would be minus 0.037. All right. Now, my question to you is, of these two, which would be the one that would be valid for our problems, for this problem?
Would it be the negative
No.
because it's less than 0?
Well, exactly. Because remember, X represents concentrations, right? You cannot have a
Right.
negative concentration.
Oh, so it'd be the 0.035.
Exactly. So the X value that we would work with would be 0.035. All right. So once we get that, then basically we can now find the concentration of, let me do it over here. We can find the concentration of each of these terms. Now, if you remember from the ICE table, the concentration of PCl5 would be equal to 1.00 minus X. And in this case, X would be equal to what we just found here. So that would be 1.00 minus 0.35. And this would be M. So when you work that out, you're going to get 0.97 M. And the concentration of PCl3 is going to be equal to the concentration of Cl2, concentration of Cl2, and that would be equal to X, which is equal to 0.035. And I made a mistake here, so let me correct that now. This here should be 0.035. So those are the answers here and here. And that's how that is done. All right. Okay, any questions about this? Any questions? Okay, so basically we're finished with the assignment. That's assignment number what, 3? So, any questions about all that we have covered? Any questions? Any questions? Going once. Going twice. Okay, so what we're going to do next is start a discussion about the next chapter, which deals with acids and bases. And you're going to see a lot of stuff that we talked about here applied to not only this chapter that we're doing, but actually for the next 2 chapters at least. All right. And also beyond, because even in thermodynamics, which we're going to do later on, some of these ideas will come into play as well. So let me get out of this here for the time being. Let me close this. Let me go to files. Oh, let me remove these. Let me clear this. Let me do this. Move this up here, and then go to files. And go to lecture notes. And we're going to talk about acids and bases. Where are you? Right here. Okay. Come on, come on, come on, come on. Okay, so let's talk about acids and bases. Okay, why is this thing taking forever to come up? Come on. Okay. So let me make this full screen. So let's talk about the characteristics of acids and bases. And you may have met some of these before. Oh, sorry. My wire is tangled up here. Oh, shucks. Okay, so acids and bases. Let's talk about that. So as I was saying, there are some properties or characteristics associated with acids that you may have met before. They usually have a sharp sour taste. And let me just say right now, while I mentioned that doesn't mean that you have to taste acids in the lab to figure out if they're acids, all right? This is just basically something that is observed. Now, there's some situations where you have actually tasted acids when you consume certain foods. So for example, vinegar, the sharp sour taste associated with vinegar is due to acetic acid that is present in vinegar. And then when it comes to certain fruits, especially citrus fruits, they have that sharp sour taste, and that is due to another acid known as citric acid. So citrus fruits, of course, would be fruits such as lemon, limes, oranges, and so on, all right? Now, in terms of a chemical property that they display, they tend to react with certain active metals to produce hydrogen gas, and they also tend to react with carbonates and bicarbonates to produce carbon dioxide gas. And this last one here, you can actually perform this experiment at home. If you take lemon juice or if you take vinegar and you add it to baking soda, which contains the bicarbonate ion, then you're going to see foaming due to gas being formed, and that gas will be carbon dioxide, all right? So that's something fun that you can try to do at home to see that reaction, all right? So that's basically, you know, a general brief description of the properties of acids. As far as bases are concerned, they're considered to be the chemical opposites of acids. They tend to have a bitter taste. And again, please do not taste anything in the lab to confirm it's a base, all right? But that is something that is documented, observed. And another thing that they display is that if you get some base between your fingers or on your skin, it may feel slippery. And again, this is something that I would not recommend that you practice in a lab. Now, the reason why it feels slippery is because, believe it or not, when the base reacts with certain oils on your skin, it produces soap, right? So we're talking about the same soap that, you know, you would use to shower with and so on. Basically, that is what is formed when you have the sodium hydroxide or the base interacting with the oils on your skin, right? So for that reason, you feel like something slippery on your skin or beneath or between your fingers, all right? Okay, now how do we define an acid? Well, the honest answer is it depends on who you ask, all right? So we're going to look at some definitions according to certain people, certain important chemists. And the first definition we're going to look at is one that is given by this guy by the name of Arrhenius. And according to Arrhenius, an acid is a substance which, when added to water, produces the hydrogen ion. Alternatively, you can say hydronium ion, because this is more reflective of what really forms in an aqueous solution when you add an acid to it, all right? So here's an example. If you add hydrogen chloride to water, you're going to end up with the hydronium ion being formed. And the reason why that happens is because this hydrogen atom here is transferred to the water molecule, and that ends up resulting in the formation of the hydronium ion, and the byproduct of this reaction will be the chloride ion, all right? So this is basically how an acid behave according to Arrhenius. Okay, I'm going to stop here and then take another break, and then we get back at 1 o'clock, and then I'm going to finish up, all right? Okay, I am back, and I'm just going to cover the beginning of this chapter for the rest of the time that we have here in the remaining 9 minutes. All right, so I talked about the Arrhenius definition of an acid just now, and this here is the definition of a base according to Arrhenius. He says that a base is a substance which produces hydroxide ion when dissolved in water, and an example of this would be ammonia, right? Ammonia reacts with water to form the ammonium ion, and as you can see here, the hydroxide ion is being formed, all right? So that's just one example. So basically, an acid is a substance which increases the amount of H+ ions present when added to water, and a base is a substance which increases the amount of hydroxide ions present in water when added to it, all right? So that's the Arrhenius definition. Now, there's another definition here by another person by the name of Bronsted, and his definition is based on whether or not a substance can give up or accept a hydrogen ion, which is the same thing as a proton, right? So according to the Bronsted definition, an acid is a substance which donates a proton to something, which is the base, because according to the definition of a base, according to Bronsted, a base is a proton acceptor, all right? So this definition does not necessarily relate to the formation of hydroxide ions in an aqueous solution. It does accept that possibility, but it's not necessary. So going back to the ammonia and water example right here, as you can see, the ammonia will be accepting a hydrogen ion from the water molecule. So this is the hydrogen ion, which will end up on the ammonia, and that results in the formation of the ammonium ion. And the byproduct of that would be the hydroxide ion. So in this particular reaction, the water would be the acid because it's donating a proton, and the ammonia would be the base because it's accepting a proton. And you're going to end up with what we call a conjugate acid, and the hydroxide would be the conjugate base, right? So basically, a conjugate acid is what is formed when a base accepts a proton, and the conjugate base is formed when an acid loses a proton, all right? So that's basically according to the Bronsted definition, all right? Okay, so with that out of the way, let's talk about what we just discussed as it applies to water and its properties. So water, if it's basically left by itself, and we're assuming that it's pure water we're dealing with, it will undergo what is called autohydrolysis. I'm going to talk to you about that, Ms. McCoy, shortly. Let me just finish this up. So this is the dissociation that will take place in pure water, water breaking up to form H+ and hydroxide ion. The name of this is called autoionization, all right? Autoionization, the autoionization of water. And if you look at it carefully, it's actually an acid-base reaction according to the Bronsted definition. Because what happens is you have two water molecules. One of them will gain the hydrogen ion from the other water molecule. And the way that happens is that this oxygen here will donate a pair of electrons to this hydrogen. So the hydrogen will give up its pair of electrons, bonding pair here, to the oxygen, and a bond will form between this oxygen and this hydrogen. And that's how you end up with the hydronium ion, and the hydroxide ion will be the other product of this reaction. So this is just showing you a ball and stick model of what's happening in this reaction. And this is basically another way of expressing this. Now, let me just say that this is more likely to be what happens in reality, where the hydronium ion is formed, because it's very unlikely that you have H+ ions by itself floating around in the aqueous solution, all right? Okay, so in this particular case, one of the water molecules will act as an acid, and the other water molecule will act as a base, and you're going to end up with the hydronium ion being the conjugate acid of the base here, and the hydroxide ion will be the conjugate base of the acid over here, all right? Okay, let's talk about the ionic product of water, and this will be the last thing we're going to talk about. So we're going back to the auto-ionization of water, as you see here. And as you can see, this is an equilibrium system, which means that we can write down a Kc expression for this. Now, because H2O is a liquid, if you remember, we said before, we can actually ignore this term in this equation here. And the reason why is because the concentration of any liquid, including water, is constant. So therefore, the result is that instead of writing Kc is equal to what we have here, we can basically simplify it and say Kw, which is the equilibrium constant we're working with, would be equal to the concentration of H plus times the concentration of hydroxide ion. So basically, in any aqueous solution, the product of the concentration of H plus and hydroxide will give you a constant, which is known as the ionic product of water constant, right? So this Kw value will be constant at a constant temperature. At 25 degrees, that Kw is equal to this value right here, 1.0 times 10 to the minus 14, all right? And this is a constant that you'll be using a whole lot when it comes to calculating some other important terms, such as pH and pOH and so on, all right? Now, this in pure water, the concentration of H plus and the concentration of hydroxide will be exactly the same. So this is what happens in pure water. And this is not only true for pure water, but other types of solutions as well. When we have this situation here, that solution is said to be neutral, right? Because the concentration of H plus and hydroxide are the same. Now, if the concentration of H plus is greater than the concentration of hydroxide, then the solution is said to be acidic. And if the reverse is true, if the concentration of H plus is less than that of hydroxide, then the solution is said to be basic, all right? However, in each of these situations, when you multiply the concentration of H plus and the concentration of OH minus at 25 degrees Celsius, that's going to be equal to a constant value, all right? Okay, I'm going to stop here for today. And I saw that somebody asked a question about the testing center. To be perfectly honest, I called him about something else and I completely forgot to ask him about what you guys were talking about in terms of being able to sign up for my test, because my course is not indicated where you have to sign up. So as soon as I finish talking to you guys, that's the first thing I'm going to do right now. All right. So that's to answer your question, Ms. McCoy. Okay. Any other questions before we go in the remaining 2 minutes?
I had a question about, or I'm the one who emailed you about my high school potentially being able to be a testing center.
Oh, yeah.
Yeah, would you be able to send me the forms / information that you have for that so I can forward it to my school and get that going?
Okay, so I can send you the form. The other stuff, I can't send it to you because that would include the test itself. Now, what I would need is an email contact with whoever is running the testing center there, so that they can, give you the test. But what I can send you, again, as soon as I finish talking to you guys, I can send you a copy of the form that I would normally complete for the testing center here. All right. So,
okay, yep.
So that I can send you, but they would have to send me something like an email or whatever. In fact, send me the entire, if you can give me somebody's name, a contact person, so I can talk to them, that would be even better.
Yeah,
in fact,
I can send you an email and a name.
Okay, please do that. Please do that as soon as you can. All right.
Yes.
Okay, any other questions, any other issues, problems? One minute. Any other questions? Okay, if there are no other questions, let me just say that I have published the videos for this chapter, so make sure you watch it, and then we'll discuss the questions associated with the assignment for that chapter, all right? Okay, so that's it for today, folks. I'll see you guys on Wednesday. All right, take care.